PSS stands for Primary Synchronization Signal and SSS stands for Secondary Synchronization Signal. The division into two signals is aimed at reducing the complexity of the cell search process. The PSS and SSS procedures are essential for the initial cell search, handover, and re-establishment processes. PSS helps the UE obtain the physical cell ID, time slot, and frame synchronization. There are 3 PSS sequences corresponding to the 3 physical layer identities within each group of cells. The PSS is mapped to 72 active subcarriers, 6 resource blocks, centered around a DC subcarrier in slot 0, subframe 0, and slot 10, subframe 5, in FDD, frequency division duplexing. SSS helps the UE obtain the cell identity group and subframe boundary. There are 168 SSS sequences corresponding to 168 possible cell identity groups. The SSS is also mapped to 72 active subcarriers, 6 resource blocks, but is shifted by half a subcarrier with respect to PSS. 3 physical layer identities and 168 cell identity groups give 504 possible PCIs, physical cell identities, in LTE. With the help of PSS and SSS, the UE can find the PCI. MIB stands for Master Information Block, which is broadcasted by the eNode B every 40 milliseconds irrespective of any user's presence. User equipment downloads the MIB from the physical broadcast channel. The MIB is the first among other system information blocks. The MIB carries very limited but essential information for UE to access the network, such as the downlink channel bandwidth, PHICH configuration, and system frame number. Additionally, the MIB also contains information about whether other SIBs are scheduled or not. SIB stands for System Information Block, which is a type of message that contains information related to network configuration, radio resource management, mobility, and access procedures. In LTE, there are 13 types of SIBs, each with its own purpose and content. These blocks are transmitted on the broadcast control channel, which is mapped onto the downlink shared channel and the physical downlink shared channel. To access an evolved node B, a user equipment needs to read at least SIB1 and SIB2. The downlink synchronization signal is broadcasted to everyone all the time, however in uplink it is not efficient, it creates lot of interference. So uplink, the synchronization process should only occur when necessary and be dedicated to a specific UE. The RACH process in LTE has 2 main purposes. 1. Achieving uplink synchronization between the UE and ENB. 2. Obtaining the resource for message 3, such as RRC connection request. There are 2 types of random access procedure, contention-based and contention-free. In contention-based random access, the UE selects one of a random access preamble from 64 preamble of a pool shared with all UEs. There are risks that multiple UEs may select the same preamble, which leads to collisions is called contention, and the RACH process that allows this type of contention is called contention-based RACH process. In this kind of contention-based RACH process, network would go through additional process at later step to resolve this contention, and this process is called contention resolution step. In contention-free random access, the eNode B allocates a dedicated random access preamble beforehand, thus ensuring different UEs use different preambles. The random access procedure consists of 4 steps. Step 1, Random Access Preamble Transmission. The UE transmits a random access preamble using the physical random access channel. Step 2, Random Access Response. The eNode B sends a random access response message using the physical downlink shared channel. The random access response message contains information such as timing advance, uplink grant, and temporary CRNTI. Step 3, RRC connection request. The UE transmits a message using the physical uplink shared channel. The message contains information about the UE's identity and capabilities, as well as the type of establishment cause for the RRC connection request. Step 4, Contention Resolution. The eNode B sends a contention resolution message using the PDSCH. The message contains the UE identity. The UE compares its identity with the received one and confirms if it has successfully completed the random access procedure.